Hey everyone, and welcome back to Build, Create and Learn, a Maker's Journey. I'm your host Stefan, and I'm really excited to dive into episode 2 with you today. If you tuned in for the first episode, you know we started things off by talking about the why behind the podcast and the project that got my gears turning, building a custom fpvdrone telemetry system. It's all about these flight stats, speed, altitude and position, transmitting down in real time, because let's be honest, for a data-hungry maker like me, flying without that information feels like leaving half the story untold. Before we jump into the nitty-gritty of microcontrollers, I've got a couple of quick updates from my maker life. First off, a new arrival in my workshop. My new 3D printer just landed, and trust me, it's already got my mind spinning with ideas for what we could build next. Maybe even some custom enclosures for the telemetry system down the line, or perhaps even some functional parts for the drone itself. It's a whole new dimension of possibilities, and I'm really excited to share more about my latest movement into 3D printing on my blog soon. Also been diving into the world of remote desktop for CAD work, trying to optimize my design workflows, and there are some fascinating possibilities there. Imagine being able to design complex parts on the go and send them straight to your 3D printer back home. But today we're really getting our hands dirty with the heart of our FPV telemetry project, tackling the STM32 microcontroller. This is where the rubber meets the road, where the theoretical becomes tangible, and where the real learning begins. Part 1. Setting up the development environment. The first steps. So the very first thing on this embedded journey was getting the STM32 Cube IDE installed on my Mac. And honestly, for a major development environment, it was surprisingly straightforward. A quick heads up for everyone else diving in though, you need to register an account with STM to download it. It's a small, quick step, but definitely good to know beforehand so you're not caught off guard. Once you're in, you immediately notice the difference from something like Arduino IDE. It feels more professional, more robust, with a lot more options. When you start a new project, you have a couple of powerful ways to select your chip. You can pick just the raw microcontroller, which gives you the maximum control, or this is the pro tip I quickly learned and would highly recommend for beginners. You can select the specific development board directly. Choosing the board has a huge benefit. All the onboard components like LEDs and buttons are often already pre-configured for you, correctly assigned to the microcontroller pins. For my nuclear board, I could immediately see the LEDs properly assigned in the configuration. It saves a significant amount of initial guesswork and head scratching trying to figure out which physical pin maps to which software register. For a project type, I recommend going with the Cube MX Auto Generation. Especially for beginners, it makes it so much easier to use the microcontroller correctly right off the gate. It handles a lot of the initial setup for you, so you can focus on your application logic rather than getting bogged down into low-level configurations. Part 2. Dive into the debugging and the printf pitfall. My very first task, once the IDE was set up, was simple. Test the printf functionality. I just wanted to make absolutely sure that the board could be programmed and compiled properly, so that I could get a debug message back to my computer. So I added the standard library and a simple printf command to my main function. Sounds easy enough, right? But then a little moment of anxiety. When I connected the board for the very first time, a message popped up. STM link debugger needs to be updated. Now, I'll admit I needed a moment to think. You know that feeling, you just started out, you're super excited and you really don't want to break the new component on day one. That thought of accidentally corrupting the firmware or damaging the chip just by trying to update it was definitely there. But I thought, deep breath, remind myself that these updates are usually routine, proceeded with it, flashing the debugger to the newest version, and thankfully it went smoothly, no hiccups. Phew! Crisis averted before it even began. So, debugger updated, code compiled, loaded onto the chip. I'm staring at my trace console, eagerly waiting for my first message, and nothing. Absolute silence. Oh no, what happened? I thought I followed the learning material exactly. I didn't do anything different. The immediate reaction is always that I've done something fundamentally wrong. I carefully rechecked my code line by line, comparing it to the example, inspecting every character, and then I saw it. A tiny problem. I had used single quotes for the printf statement. In TypeScript and Python, which I've been working a lot in the recent years, that difference is completely irrelevant. Single or double quotes, it doesn't matter. But C is notoriously strict about these details. One tiny change to double quotes, recompiling and reloading, and there it was, my first successful message in the tracing console. Yes, this relief was absolutely real. A small victory that felt disproportionately large after this brief moment of panic. It's the little moments of overcoming unexpected hurdles that makes the maker's journey so rewarding. Part 3. My learning process and the Blinky milestone. This experience with the printf bug really highlighted my learning process and how I approach new technical challenges. For quick starts and getting something like the Blinky app up and running, YouTube videos are fantastic. You are visually following along, get a quick overview and see immediate results. They are great for the initial spark and getting the feet wet. But to go deeper to really understand why things work the way they do, how memory addresses are structured and how to find the right ones for the job, I've been heavily relying on a Udemy course, Mastering Microcontrollers and Embedded Driver Development. This course dives into the nitty-gritty details that YouTube tutorials often gloss over. It's about understanding the foundational principles. Using the hardware abstraction layer simplifies a lot the tedious memory fiddling and direct register manipulation. I firmly believe it's worth understanding how it works at least once before relying solely on the abstraction. It gives you a deeper appreciation of what the hardware abstraction layer is doing for you and helps you troubleshoot when things inevitably go wrong. This deep dive into the fundamentals is what really helped me navigate datasheets and find the necessary information, turning what initially looked like an impenetrable wall of text into something that I could actually learn from. I can totally recommend this course. It's incredibly well made, clear and comprehensive. As for the Blinky app itself, after a printf debugging saga, it was fairly straightforward. Just 2 lines of code in the main function to toggle an onboard LED on and off. No big surprise, no dramatic revelation, but seeing the LED light up exactly as configured, blinking away in a perfect rhythm was pretty satisfying. It's the hello world of an embedded system and it always feels good to get the first successful interaction with the hardware. Part 4. Connecting the first sensor, the BME280 journey. With the Blinky app out of the way, the next big step was connecting our first sensor. I had my breakout board ready and my STM32 was up and running. But before I could even connect it, there was the small but significant hurdle, soldering the pins onto the breakout board. It's common practice for these tiny breakout boards to ship without the pin headers attached. It reduces the shipping footprint and gives you more options for how you want to mount them. But honestly, for me this was a new situation. In the past, all the sensors and breakout boards I've bought had the pins pre-attached. Now, the soldering itself wasn't the issue. I know how to do this well enough. My only open question was, which way do these pins go? Do they point up or down? After watching a quick YouTube video, it was obvious. Sometimes you just need to see it once and then it's clear. A little visual guidance goes a long way. Oh, a little maker tip for soldering this. I actually 3D printed a breadboard replica. It's perfect for holding the pins straight up while you solder, and it meant I wouldn't accidentally damage one of my actual breadboards with heat or stray solder. Though after doing it, I'm still a little unsure if I put it into the right direction, because now the sensor itself points up, but the labels are at the bottom. It works, so I'm rolling with it for now. So, pins soldered, board ready. Next big question, how to connect them properly. My BME280 environmental sensor breakout board has the following pins: VCC, ground, SCL, SDA, CSB and SDO. I logged into the BME280 datasheet and the first thing I learned was the sensor supports 2 different data protocols, I2C and SPI. For beginners, I2C is generally recommended because it uses fewer pins and it's often simpler to get started with. So that's the path I took. I spent some time learning about the I2C protocol, understanding how it transmits data between devices and the concept of master and slave devices. For wiring it up to the STM32, I also needed 2 pull-up resistors between 3.3 volt and the clock and the data lines. The datasheet recommends 4700 ohm resistors, but the closest I had on hand were 5100 ohm ones. Close enough, I thought. That should be fine for the first test. It's often about making it work with what you have in the maker's world. I watched several videos, but most of them covered Arduino and ESP32 setups, and they often used pre-made libraries that were directly helpful for my STM project. It was a bit frustrating, feeling like it was constantly hitting dead ends for my specific setup. But then I got lucky. I found a tutorial that used STM32 blue pill board with the exact same sensor, although with a slightly different breakout board. Crucially, this developer also provided a very sophisticated driver for this sensor and a detailed explanation of the code he wrote. It was a lifesaver. I used his code files and imported them to my project. The first thing I needed to adjust was linking it to the right chip header file from my nucleus board, but after a first build, everything looked good. Now the moment of truth. I integrate this driver into my main program, followed the tutorial on how to set up and configure the sensor, creating a new debug configuration and started the program in debug mode. I looked at the live expressions just like the developers in the video did, but for me it only showed 0 values, absolute zeros. This couldn't be right. I double checked the wiring, tracing every connection, and then it hit me. I understood a potential conflict. I was using the pin diagram from the embedded.com platform for my nucleus board, which is a great resource, but it turned out that the SCL and SDA ports on my specific board were swapped compared to the pin diagram. So I gave it a try and switched the two cables from PC9 and PC8. And then, hooray! I saw live data values appearing on the screen. Temperature, pressure, humidity. It was truly a fascinating moment. Seeing these numbers, real world data populating on my debug console. After all, the setup and troubleshooting was incredibly satisfying. I know I didn't write the entire driver myself, and there are definitely many parts of the code I don't fully understand yet. But it works, and that makes me incredibly happy. It's a testament to the power of open source contributions and building on the work of others. Since I'm primarily interested in altitude values instead of raw pressure data, I definitely wanted to add this myself. I looked up the calculation for converting the measured pressure to sea level heights, a quick bit of research into atmospheric models, and after a few minutes of coding, I also had my desired altitude values. It felt great to add my little piece of logic to the system. I know I've only briefly touched on all the capabilities of this one sensor and its configuration, but as a first step I'm really happy with the results. This first test was also configured for indoor measurements, so for drone flights outside I definitely have to tweak the sampling configuration settings to account for dynamic changes in environment. Part 5, conclusion and what's next. So this episode has been all about these critical first steps, getting our development environment set up, wrestling with debuggers, appreciating datasheets and celebrating the simple joy of a blinking LED. And then the big win, getting your first real-world data from the BME 280 sensor, even after a little pin swapping adventure and a quick 3D printing detour. It's a powerful reminder that Maker's journey is full of these small aha moments, tiny frustrations that led to big lessons and simple victories that fuel the motivation. It's about learning, adapting and most importantly, not being afraid to stumble and figure things out along the way. That's where the real growth happens. Next time, the goal is to get some useful GPS coordinates. That's going to be a whole new challenge, dealing with different data formats, understanding satellite signals and ensuring accuracy for the drone telemetry. It's about the big pieces of the puzzle and I'm excited to share these ups and downs of the process with you. If you enjoy this honest look on the early stage of an embedded project, please subscribe to Build, Create and Learn a Maker's Journey wherever you get this podcast. Drop me a message, connect on social media or leave a comment on the blog post in the episode. I would love to hear about your debugging nightmares. Your stories are what makes this community so vibrant. Let's keep building, creating and learning together.